So fibers, what do you build with them? How do you build something cool with them? And the main thing is you need a scheduler. So in the kernel schedules threads. We want to run a bunch of different fibers at once, so we need a scheduler for fibers. So there's a scheduler object that's abstract. Your main method on it is to schedule. You schedule either a fiber or any sort of callable object, a boost function, a functor of any type, an object that you can call, and that function will become the root of a new fiber when it gets executed. So schedule just adds it to a list of fibers to be executed, and whenever a fiber wants to yield, like it's going to block, it yields directly to the scheduler. And the scheduler just looks at its list and selects the next one. It's a simple first in, first out queue. The good thing about it is it's n-threaded. So a scheduler can run fibers on one thread, or it can run it on as many threads as you want. It makes it so that you can divide the workload and you just schedule it. You don't care where this fiber gets executed as long as it gets executed. The other feature is called hijacking. So a scheduler that hijacks its current thread means that it doesn't really own the thread. If you start 5 threads, the scheduler will start 5 threads of its own. Or it can hijack the current thread as one of its threads so that you don't have to worry about calling schedule to do something. A hijacking scheduler, it suddenly is just running, and you can do things that will yield to the scheduler and it will yield back correctly. It just makes the simple examples really, really simple because you don't have to worry about getting onto the scheduler somehow. There's multiple scheduler implementations, and they differ in what they do when there's no work to be done. So when there's no fibers queued up, they all go to an idle function. The main two are IO Manager and Worker Pool. The IO Manager is platform specific. There's IO Manager IO completion ports for Windows, IO Manager KQ for BSD systems, and IO Manager ePool for Linux systems. And what they do is in that idle function, they handle OS level events. So your non-blocking IO. They wait for those events to come in. You register with the IO Manager saying, I want you to reschedule my fiber when this event happens. And that's the basis for the IO in Mordor, is using an IO Manager. The other one is a worker pool, which is just a generic thread pool. Typically, you'll have one IO Manager and then any number of worker pools for however you want to divide up your work. Worker pool just has a generic thread pool. Its idle function just basically waits on a semaphore waiting for more work to be scheduled on this worker pool. So leveraging schedulers. The scheduler has 2 static methods. One is yield. And yielding to a scheduler is like doing a yield in a thread. It says, I want other work to happen right now, and when you're ready, schedule me again so that I can run. The other one is yield to, which says, okay, scheduler, you take over, you execute other fibers, I'm done, but don't reschedule me. Somebody else is going to reschedule me at some point. For example, the IO Manager. When the IO completes, so a typical flow for asynchronous IO is you register with the IO Manager, say I'm about to do this asynchronous IO, you execute the operating system function to do the IO, and then you yield to the IO Manager, to the scheduler, which will reschedule you when the IO completes. And it makes it very simple. A very cool function is switch to. And a helper is a scheduler switcher. Switch to takes your fiber. You're running on one scheduler. When it exits from switch to, when it returns, you will then be running on another scheduler. So if you're doing work in the IO Manager that you don't want to block, but then you need to do disk IO, which will block, you can switch to a different thread pool and not have to worry about doing any callbacks or anything. Just you call switch to and you're there. Scheduler switcher is just a helper function that does that on its constructor, and in its destructor it returns to the original scheduler, so that if any exception happens, you return to the same context that you were originally. Then there's helper functions parallel do and parallel for each, which are how you parallelize things. They schedule a bunch of fibers at once, and then they wait for them all to complete before they return. You can use it in a single-threaded mode. So if your I/O manager just has a single thread, it will parallelize things because those fibers will yield to the I/O manager and allow other fibers to execute at the same time.